All right, so let's talk about the physics of motion. In particular, let's talk about the kinematics. Kinematics is study of motion, and I want to talk about the study of motion in 3 dimensions using vectors. So to start with, the thing that's really nice about vectors is they allow us to give really nice, clean, relatively elegant definitions of these things. Position is just a vector-valued function of time. To get the velocity, we differentiate with respect to time. That gives us the velocity of the particle. The acceleration, we just differentiate again. That gives us the acceleration. So the derivative of the velocity with respect to position is with respect to time is the acceleration. The derivative of the position with respect to the time is the velocity. Position, velocity, and acceleration, all three of these are naturally understood as vectors. In fact, vector-valued functions of time. We can also talk about displacement sometimes. That's like also a vector. It tells you how to get from here to there. Speed is the magnitude of the velocity, as we've discussed. It's also the instantaneous rate of change of the arc length with respect to time. As such, if we integrate it, we get the net arc length from time 1 to time 2. So the net arc length subtended over some time interval is also known as the distance traveled over that duration, over that time interval. And then we can do some deeper things once we've got the words settled here. Let's try to understand how this squares with our previous discussion of T and B. To start with, I would point out that the velocity can be written as the speed times the unit tangent. This is pretty much immediately clear once you understand that the unit tangent is 1 over the speed times the velocity. So that means the velocity is the speed times the unit tangent. And I'll write it either with V or with S dot just because, well, to confuse the students, of course. I'm just joking, mostly. Now, the acceleration, dv dt, right, is equal to, I guess I should include that in my musings here. A for acceleration is dv dt, but it's also the derivative of the product of speed and the unit tangent, which by the product rule gives me s double dot times t plus s dot times dt dt, right? And all right, well that's great. So that's s double dot times t, and then dt dt we can trade for the curvature times the speed times the normal. That's one of our Frenet-Serre equations. And so this calculation shows you that the acceleration only has a tangential and a normal component. There is no binormal component to the acceleration. That's kind of interesting. But there's more. We can clean this formula up and see what we got. We've got s double dot for the component of t. We've got curvature times s dot squared, or curvature times v squared for the normal component. And so that's worth noting. Tangential acceleration we can calculate just from calculating the second derivative in the speed, whereas the normal acceleration is given by the curvature times the speed squared. You might recognize this written as v squared over r in physics. Oftentimes we just talk about circles. So in the context of a circle, the curvature is 1 over r, and this just becomes v squared over r. Another useful thing to know for working problems is that the tangent and the normal are perpendicular, which means that the length of the acceleration squared is equal to the tangential component squared plus the normal component squared. So this equation is nice and handy to have if you have calculated one of these but don't feel like finding the other. It's usually pretty easy to find the magnitude of the acceleration, whereas actually directly calculating the normal component would require calculating the curvature, which for an arbitrary curve we've seen is kind of daunting. That's a pretty hard problem. So let me just give you an example here, a brand new, just for you guys example, and then I'll get back into the notes. And I've got some pretty pictures I should at least spend a minute looking at with you. So here's an example. Given that the velocity is, make sure we're in frame. We were kind of in frame. So given that the velocity is t squared, cosine t, sine 6t, and the position at time equal to 1 is 4, 0, 0, find the position and acceleration as a function of time. And then also find the tangential and the normal acceleration. All right? So first order of business, acceleration. That is a piece of cake. All you got to do is just differentiate this. So 2t minus sine t, chain rule 6 cosine 6t, right? Bam, we're done. Great. Now, position, on the other hand, we can get from integration. I've decided to use a definite integration to do this problem. Of course, you could also do an indefinite integration where you add a constant vector and then fit the constant vector to the given data. It's up to you which way you want to do it. I just decided to do it this way for the sake of showing you, in case you hadn't seen this before. So integrate from 1 to t dr d tau d tau, and that's the same as the integral from 1 to t of v of tau d tau, because v of t is that. But I have a formula for this, right here, and as such, on the other hand, on the flip side, on the other side, by the fundamental theorem of calculus, that's r of t minus r of 1. That was one of the things we learned in the calculus of curves section of the notes. And as such, we can rewrite that r of t is r of 1 plus this, because when we integrate that, we get that. And cleaning it up a bit, there it is. The position is 400 plus 1/3 t cubed minus 1 times the sine of, comma, sine of t minus sine of 1, comma, minus 1, 6 times the quantity cosine 6t minus cosine of 6. And that's a perfectly good answer. I don't really feel any obligation to add these vectors. It doesn't. There you go. That's the position at time t. Don't ask me to visualize that, although with mathematical software, of course, we could if we were so inclined. Now that I have that, I can try to find a sub t and a sub n, right? So to find a sub t, make sure I can see what I'm doing. So keep in mind that the acceleration is what it is up here, okay? I'm going to put that out of frame now. So first of all, the speed is the magnitude of the velocity, which t to the fourth plus cosine squared t plus sine squared 6t. Tell you what I'm going to do. I'm going to zoom out a bit. I think that's the better solution here. That way you can see everything. A little bit smaller, but there it is. So, so the speed is the magnitude of the velocity. I just calculate the square root of the sums of the squares. But then the tangential component is the derivative of the speed, which means I have to differentiate this monstrosity with respect to time, which we can do. It's just unpleasant. So chain rule gives me 4t cubed minus 2 sine cosine plus 12 cosine 6t sine 6t, all divided by 2 times the square root of this stuff. So there you go. There is the tangential acceleration for this curve, rather this path. I say path because when I think about a path, I think about time dependence in this course. When I think about a curve, I think about a set of points. A given set of points, we could find many different paths to cover. That's the language I try to stick with. And these, the difference between what's a path and what's a curve, there's not universal agreement about this. So my apologies for that, but I can't make everyone use one language, Mathematicians mean different things. One mathematician's path might be another mathematician's curve, and you just got to follow the start of it and find out what they mean to be precise. Anyway, the normal component we can get from the square root of a squared minus t squared, because remember, this is just coming from a squared. The magnitude of the acceleration is the tangential component squared plus the normal component squared, and that's true because the tangential and the normal give you perpendicular components, and so we can calculate the length of the whole vector by taking the sums of the squares of the components and square rooting. And anyway, there you go. That's the normal component to the acceleration. And I don't really feel inclined to simplify that. There it is. So you can imagine that the curvature... See, this is maybe kind of a really kind of circuitous way to calculate the curvature as well, right? Because the normal component's also equal to what? It's also equal to the curvature times what? I've already forgotten. Normal component is the curvature times v squared, right? So actually, it's kind of sneaky, but we've calculated the curvature of this curve. If we just take the above and divide by the speed squared, there you go. We've almost got the curvature. So yeah, you can try to calculate the torsion if you want, but I don't think they pay me enough to do it. Torsion's hard. So I have some relatively pretty pictures in here I'll share with you. So here's the definition I just told you a second ago, and you know, I start by calculating velocity and acceleration for something just going in a circle with constant angular rate of change. In that case, there's no tangential component to the acceleration, and like the acceleration is, I'm going to zoom in a bit here, maybe. So there's no tangential component to the acceleration. The acceleration's just center seeking, right? It's just got that normal component. So okay. Another example is just this rather famous one in physics. The acceleration is zero minus g. In other words, acceleration is downward pointing. So I integrate again. I find the position as a function of time, and then you know, here it is: x naught plus v naught xt, v naught y naught plus y naught t minus 1/2 gt squared. So constant velocity x motion, accelerated y motion, of course, because the gravity is in the y direction in this current setup. And here's a picture. So I've got the velocity vectors in green, and in every case the acceleration points down, right? So sometimes the acceleration has just a normal component. Sometimes the acceleration has a mixture of normal and tangential components. In this picture, the acceleration is purely normal right at the top, but elsewhere there's a bit of each. So now next I discuss, you know, displacement, distance traveled, all that good stuff, and I go ahead and calculate the arc length for circular motion, and hello? It's exciting phone call about student loans. My apology for interrupting your video. This office has many distractions. That is the chief one among them. Next example, I just have a circular motion, but this time I don't assume that the angle is just like a linear function of time. I say the angle could be quadratic in time, and I work it out, and we get this time that the arc length is r naught omega naught t plus 1/2 r alpha t squared. So like there's an angular acceleration term in the arc length, and you might have seen some of these things when you took physics, but I'm going to go on. I mean, that's not really the point of this course, but the point of this example is to connect with high school physics formulas if you remember them or not. Here's a picture. In the case that the acceleration is not, in the case that the circular motion doesn't have constant speed, you know, that means that there's a tangential component to the acceleration. And so you can break up the acceleration into like the center seeking part and then the tangential part, which is in the direction of the velocity. So generally speaking, for non-uniform circular motion, there's a kind of a mixture of tangential and centripetal part. This example 2.38, I began as I wanted to give an example where I showed an arc length which was interesting, but you couldn't explicitly calculate. And then I was able to calculate it, so it kind of backfired on me. But this integral was difficult enough that I just kept it because I was really surprised I could actually get to the end of it. Here's the formula for the arc length of a parabola coming from parabolic motion with initial velocity x and initial velocity v naught y. So this is the x component, y component of the velocity. And yeah, there's the arc length of of this is given by that. So yeah, of course, if the initial x velocity is 0, then it's easier. But, sorry, I'll stop showing and telling here pretty soon. I just wanted to point out this is a good example. I just have, I give you position, I find velocity, acceleration, speed. Nice example. Here's another one. I give you velocity, I find the acceleration by differentiation, and I integrate to get the position. That's just like the one I showed you. This example here, I give you the acceleration, I give you the initial position, the initial velocity, and so we have to integrate once to get velocity and then integrate again to get position. Another good test question. And then this again is a throwback to high school physics, basically. This one here is a good example in the sense that I actually show you how to calculate tangential and normal components of the acceleration again. So I start with the position, I differentiate, get velocity, and then once I have velocity I can get the unit tangent, and then I can differentiate again to get t prime, and so the magnitude of t prime, then I get the normal vector. Actually, so this is the less clever way to calculate a sub t and a sub n. The way I did the example at the start of this talk is probably faster than what I'm doing here. You can try both if you want, but here I just took the sort of heavy-handed approach of explicitly finding t, explicitly finding n, and then just taking dot products to find a sub t and a sub n. I mean, that's also a method, all right? Here's the derivation I went through at the start of class. Is this a class? I don't know, but at the start of this video. And so, yeah. And then finally, in the ones I've posted for you, I also have Keplers Laws derived in handwritten notes. You can look at those if you want. I'm not really holding you responsible for those calculations. I just think it's interesting to see Kepler's laws derived in essentially a course that everyone can take. Anyone who goes to university has calculus, gets to this point. Most people, reasonably intelligent people, can get to this point in their life, and they can actually understand the derivation of Kepler's laws. I don't think we pause to understand how significant and wonderful that is, that we can appreciate the derivation of Kepler's laws. As I'm not a genius. Some of you might be. I don't know, but these were deep truths that were hidden only to the deepest intellects a couple hundred years ago. I mean, Kepler's laws were first derived through careful study of astronomical data for years and years. Tycho Brahe, his data, and then Kepler fit ellipses to that data for no particular reason except that it worked. And then a little bit later, Newton came along and probably found the derivation that's in my notes, something like that. And when Newton did that gave it supported the the contention that gravity followed an inverse square law and could describe planetary motion. So I don't know. I think these things are really neat. But I also point out these problems. There are nice problems here, and there are solutions posted to those problems as always. So, but I think there's one more section I need to talk about in this part of the course, which is how to integrate along a curve. I'll do that next. Thanks.